Hey guys, welcome to Pre-Calc Lesson 12.10, Limits to Infinity and Beyond. A little math humor. Okay, so we are going to establish three limit rules as x approaches infinity. Now, the first one you see here is the limit of x as x approaches infinity. Well, if you think back to the first time we started evaluating limits, we said, well, do direct substitution. So direct substitution would give us that this limit is equal to infinity. So what happens here graphically as x approaches infinity, remember limits the y value, y approaches infinity. So we have some function that looks like this. Okay, well, our next one, limit of 1 over x as x approaches infinity. So again, here we're going to do direct substitution. Well, if I do direct substitution, I've got something that says 1 over infinity. What is 1 over infinity? Now, if you take your calculator, unfortunately I can't show you this in the video, but if you take your calculator and do 1 divided by 1, well, that's 1. 1 divided by 10, 0.1. 1 divided by 100, 0.01, so on and so forth. What happens to the value of the fraction as that denominator gets bigger and bigger and bigger? Well, what happens is that approaches 0. It turns out that 1 over infinity is equal to 0. So what happens in this case? Well, what this says is as x approaches infinity, so as we move to the right, the y value is going to approach 0. So it's going to look something like this. As we move to the right, the y value gets closer and closer to 0. Okay, and our last one. The limit as x approaches infinity of c. Well, if you notice here, that's c, that's x. There is no x in this expression. That is just a constant. So the limit of any constant is simply the constant. So what this is going to look like as x approaches infinity, that y value is going to stay exactly the same. So that's going to look like a horizontal line. Okay, so those are the three big limit rules as x approaches infinity. We need to know those. The limit of x as x approaches infinity is simply infinity. The limit of 1 over x as x approaches infinity is 0. And the limit of a constant as x approaches infinity is simply that constant. Our first method for finding limits as x approaches infinity is we are going to take the original expression and we are going to divide each term by the variable with the greatest exponent in the denominator. All right. So, and this part's important, in the denominator. So in our first example here, I'm going to look at this expression. I want to take the limit as x approaches infinity. I'm going to take a look at my denominator and take a look at the variable that's got the greatest exponent. So that's going to be this x squared. So now what I'm going to do is I'm going to take that expression, I'm going to do it down here, I'm going to divide each one of those terms by the x squared. And really what we're doing, all right, is we're taking this expression, we're multiplying it by 1 over x squared over 1 over x squared. All right, this is just a little bit of a shortcut here that's going to allow us to do this. So it's going to be 3x over x squared plus 5 over x squared all over x squared over x squared plus 7x over x squared plus 12 over x squared. So now what I'm going to do is I'm going to simplify this expression as much as possible. All right, I'm going to bring it back up here. I'm going to take the limit as x approaches infinity of the expression I get when I simplify as much as I can these terms. Okay, well, in the first one here, this x would cancel with one of those, so that's going to give me a 3 over x. Plus, there's nothing to simplify in the next one, that's just 5 over x squared. Over, this cancels. Now, don't forget, that's a 1. That's not a 0. That's a 1, so it's going to be 1 plus this x here cancels one of those, 7 over x, plus 12 over x squared. Okay, well, how do I take this limit? Well, if you remember our rules, if you have an x, as x approaches infinity, that's just going to become an infinity. 1 over x, or 1 over x squared, or 1 over x cubed, or 1 over x to the fourth, it doesn't matter. As x approaches infinity, that's going to give us a 0. And the limit of a constant is just going to be that constant, again, as x approaches infinity. So now what I'm going to do over here is I'm going to take my individual pieces, I'm going to take those limits. 3 over x. Well, I don't care what this is. I don't care if it's 3 over infinity or 10 over infinity. If I have an x in the denominator, that's going to be a 0. So this limit right here, that's going to be a 0. 5 over x squared. Well, again, that's going to be a 0. The limit as x approaches infinity of 1 is just 1. That's going to be a 0, and that's going to be a 0. So in my numerator, I'm going to have 0 plus 0, which is 0. Denominator, I'm going to have 1 plus 0, which is 1. That limit is just going to be 0. Let's take a look at another example. All right, in this one, you can see here that I need to do a little bit of work in that denominator before I can go ahead and divide everything by what will end up being an x squared. So remember, if you multiply this out, x minus 2 times x minus 2, that's going to be x squared minus 4x plus 4. So now I'm going to take that expression and I'm going to divide everything by x squared. All right, so let's write that out. I get 3x squared over x squared plus 2 over x squared all over x squared over x squared minus 4x over x squared plus 4 over x squared. Okay, so I'm going to bring that back up here. Limit as x approaches infinity of, let's see what happens here. Those cancel out. All right, so that's just going to give me a 3 plus 2 over x squared over, what's going to happen here? Those cancel. That's going to give me a 1 minus, what happens here is that cancels with one of those. That's going to be 4 over x plus 4 over x squared. So it's a lot of algebra, all right? And that's actually the hardest part of this whole limit problem, is doing that algebra, because my limit properties are pretty straightforward. Remember what we said. The limit as x approaches infinity of a constant is just that constant. So that's just going to give me a 3 plus, well, since I have an x squared in the denominator, that limit's just going to be a 0. All right, so it's going to be 0 over, again, that's just a constant, so that'll be 1. And then these others are going to be zeros. So this limit ends up being 3 over 1, or just 3. The second method we have for finding limits to infinity, it's going to be the method that you guys pretty much use all the time. I know it looks a little bit daunting here, but it's really kind of a simple concept. So first of all, if you've got a rational function and the degree of the numerator is greater than the degree of the denominator, the limit of f of x as x approaches infinity is going to be infinity, or you can say does not exist. If the degree of the numerator is less than the degree of the denominator, so the degree of the denominator is greater, then that limit as x approaches infinity of f of x is going to be 0. And the third scenario is if the degree of the numerator equals the degree of the denominator, the limit of that function as x approaches infinity is simply the ratio of the leading coefficients. All right, so let's take a look at those three scenarios. So right here, number 1, obviously this is going to match up with number 1 from up above. What I'm noticing here is that in this rational expression, the numerator has got the variable with the highest degree, x squared. Well, I don't even care what else is in that problem. If the greatest degree is in the numerator, I'm going to say that limit is infinity, or the limit itself does not exist. In example 2, this kind of matches up with number 2 from up above. What I notice here is that the denominator has the variable with the highest exponent, so everything else goes away. Well, if that's in the denominator, 1 over infinity is 0, so that limit is going to be 0. And our third case right here, what I notice, I have an x squared in the numerator, I have an x squared in the denominator. Everything else goes away. Well, what happens here is that I'm going to take the ratio of those coefficients. So I kind of wrote over it, but that was a 2, and that's a 1. So I've got 2 over 1. So the limit as x approaches infinity here is 2 over 1, or just 2. All right, let's put it into practice. These are going to go very quick. So this one right here is actually probably the most complicated of the next 3 we're going to do. And I want to kind of go back and review some operations of limits that we had. This ideally would be a single rational expression. But if it's broken up like this, what we can do is simply use our properties of limits and say this is going to be the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 5 over x. Now, if you remember from earlier, this is just a constant, so I don't care what x is, that limit is just going to be 2. So this is going to be 2 minus, and here we go. The denominator has the largest degree, so that's just going to be a 0. So the limit as x approaches infinity of that is going to be 0. 2 minus 0 is just 2. So the next few that we're going to do, we'll have a single rational expression here. And what I need to pay attention to is where is the largest degree of x? Well, it's the same. So if it's the same in the top and the bottom, basically what we do is we ignore everything else. And then I take the ratio of these coefficients right here. So the limit as x goes to infinity of this expression is going to be negative 2 over 3. And obviously I can't simplify that anymore, so I'm just going to leave that negative 2/3. Okay, next one. Limit as x approaches infinity. So again, when we see this, we're thinking the largest power of x, or a variable. So as I search through this expression here, I notice I have an x cubed in the numerator. There's no x cubed in the denominator, so that's what I'm going to focus on right there. So basically, you can ignore all these other terms. Well, since that's in the numerator, I'm going to say that the limit as x approaches infinity is going to be infinity, or I can say that the limit does not exist. You're going to see both of these as choices. You'll never see both in the same problem, but these really kind of represent the same thing. I just want to take a second here to talk about graphically what's happening. I have no idea what this graph looks like right now, but I know one thing. As x approaches infinity, y approaches infinity. So I do know that the graph's going to, at some point, end up going like this. And that's all I know. That's all that tells me. So we in pre-calc generally use does not exist, but when you go on into calculus, the teachers there want you to narrow that down a little bit more and determine the behavior, the end behavior of that graph. Okay, last one. All right, so in this rational expression here, I just wanted you to be careful of one thing. We see this from time to time, and it's really more of like one of those gotcha questions. At first glance, you might think that you're going to take the ratio of these coefficients, but they don't always give you each expression in standard form. Notice they put the x squared here. All right, that's just really to try and trick you. That's the largest exponent, so it has a degree of 2, which is greater than everything else. So everything else except for this will go away. So now this ends up being 1 over infinity, which we've talked about earlier, is just 0. Okay? All right, so that concludes our lesson on limits to infinity. Like I said, method 1 is really good for practicing our algebra skills and kind of letting you understand where this sort of shortcut comes from. But I'm sure most of you are going to prefer to kind of memorize these rules here and apply it to the expressions. Okay, as usual, if you have any questions, feel free to reach out